right, so I want to start with this one, importing DILs, and it turns out this one is okay to do on an ARM-based machine. So I downloaded the file we're going to work with here, which is a very simple file. In my downloads folder, it's hello4, and all right, I guess I got to download it again. Thought I had it, but anyway, let me get it here. Copy this, copy link, let's bring it down. I wonder, there's probably some way to get this sorting turned off. But anyway, sort by nothing, that's what I want. Group by nothing, that's a good start. Okay, and now it's really not there. Okay, so I'll bring up Firefox and download this thing. There. Okay, now it's there. Now, I can run this thing. Let's run it in a command prompt. Okay, go into downloads. And I think I can make this bigger. Very nice. Okay, so there is a thing called Hello4. And all it does is print a couple lines of text, one line, and then come back. So it's really just a hello world program. All right. Now I want to examine the import address table for that program. So I use PE view and go to downloads, and there it is. All right. And so I'll make this all bigger. All right. So if I look at the import address table, it's in the R data section. Maybe it's the I data. Guess it's the I data section. There's the import address table. So you can see the API calls that it makes in the Windows API and the library. Everything it uses is in kernel 32. And you can see it uses a couple of dozen of API calls in kernel 32. Now, the DIL name, like I say, they're all from kernel32.dil here. And you can understand the addresses if you go to iData here. All right, let's go back to our list. The last API function in the list is raise exception, and it has a P file of 5954C and a number here, a data of 5D9DA, which is very close to, yep, okay. And so you can see it here. If you notice this address, 5954C, you can look at the section raw here, and 54C is here, and there you have in little endian order the address 0005D9DA, which was the data. So that's what this is. This is a table of pointers to those functions. All right, a lookup table. All right, and you can look at the import hints and DIL names here, and you'll find that raise exception is here, and it's going to be at that address 59D E0. Here's raise exception. You can see it there. So that's what's going on. That's how the libraries are referred to here. And if the 5D 9DA, the address that's stored there, is a relative virtual address, location in RAM of the object relative to its base address. If you look at the iData header up here, you will see the relative virtual address of the section 5D1000 and the pointer to the raw data 594,000. So this is just the thing here, just to understand all these pointers and how it works. And the image base address is here in the image NT headers, the image optional header. Here's the image base. And like I say, by default, all executable programs want to load at 400,000 in hex. That's where they want to load. That's going to be a virtual address. They're all going to think they're running there. So if you run this program in Ollie debug, oops, I missed something there, Ollie debug, and load it, downloads, hello4. Okay, and now you view the memory map. here it is, but it's not at 400,000. It's at 710,000. And that's the consequence of address space layout randomization, which was added to Windows in Windows Vista and all later versions to make it harder to exploit them, which we'll be doing tomorrow. To exploit a box, you typically find a buffer overflow, you inject code, and then you jump into the code you injected. But you have to know where it is. So you have to know where the program is loaded in memory. So randomly relocating a program in memory makes it more difficult to exploit. So it turns out when you're analyzing malware and any program really, this is a big annoyance, this randomization, and you can turn it off. And that's what we're going to do here. So you can use this program called setDill characteristics. You could also just use a hex editor. It's just a bit you're changing in the header. But anyway, let me go to downloads where that program lives and setDill characteristics. There. I should have hello 4 here. And I do. So I can use setDill characteristics there and just do -D to turn off. If I run it without any it'll show you the options. -D will clear the dynamic base flag, which means this program is no longer using address space layout randomization. You can also turn off data execution prevention and an integrity check. So here, I'm just going to do a -D on hello 4. And there it goes. And now, when I run hello 4, it will load at the default address. So let's run it in Ollie again so we can see. Okay. All right, there's hello 4. And when I view the memory map, now here it is loading at 400,000, the default location. This will turn out to make it a lot easier to analyze defective programs and fix them. And if you look at the rest of this project, that's what you have to do. So once you understand what these addresses are and how the libraries are loaded, then I have a variety of challenges here for students to do. The first one, you open this thing and just find an address in the existing program. And the next couple, you're going to have to fix these programs. You find another DIL, and some of them are broken. And you'll have to find the missing DIL name or other flaw and fix it by modifying the file. I've just taken a working file and then used a hex editor to break parts of it. So you can find the part. And it turns out that that program we saw last time, CFF Explorer, is very useful for this. When you open a broken file, it highlights in red the number that makes no sense. So if you have a really bad mistake, it can catch it pretty well. All right, so let me stop this video and make it.